Hi, I'm Huizi from Stanford University. Today I'm going to give a brief overview of CaTDet, an efficient system for video object detection. So first, what is video object detection? The goal of video object detection is essentially to locate and classify objects in a video stream. As shown in this example, there are 4 objects detected from an image, and 3 of them are pedestrians labeled in yellow boxes, and 1 of them are car in red box. And one major difficulty of video object detection is that it's rather compute intensive. For example, a very expensive GPU can only process medium-sized image at 19 frames per second, while a very cheap camera can easily generate high-resolution video streams at 30 frames per second. And imagine how many cameras do we need for some real-world applications like autonomous driving? Well, it requires multiple cameras. So are we gonna stack like 10 GPU cards on every self-driving car? Hopefully not. So to make it practical for real-world applications, we need to develop some efficient algorithms for video object detection. And before delving into the details of our system design, we would like first to think about the properties of video. So there are 2 types of localities that exist for most of the objects in a video. The first is temporal locality, which means an existing objects tend to appear again in the near future. And the other one is spatial locality. If an object appears again, then it tends to appear in a nearby location. And these 2 localities are quite obvious, right? But how are we gonna exploit them to make it more efficient for video object detection? And our answer is quite simple, that we should avoid redetection and do calibration as much as possible. So redetection is expensive because we will need to run a very large detector model all over the place on the whole image, while calibration can be much cheaper because if we have already know the rough location of some objects, we can only run this convolutional neural network model on selected regions, therefore greatly reduces the computation cost. And CaTDet is based on such simple concept. And we now talk about the design of CaTDet system. So first, we would like to start with some standard detect-to-track pipeline. So in this pipeline, the detector takes images 1 by 1 and outputs the detections for each individual images. Here, a detection means the bounding box surrounding some physical object and the class label associated with it. And later, once the detections of multiple frames are ready, it's fed into some post-processing step, like a tracker, and the tracker links the detections into tracklets. So why are we talking about this? As we have mentioned before, we want to exploit the locality of the video by estimating the rough locations of previous objects. So we figured out that the tracker is actually a good candidate for this goal. Now think about the standard tracker. The goal is to link detections, and to do that, it will need to predict the future locations of existing objects and then solve a matching problem. And for our tracker, it's kind of reversed. So we are trying to predict the future locations, and to do that, we will need to link detections and estimate informations like the motion and change of scale. And so the advantage of that is that we can borrow some well-studied popular tracking algorithms with little modification and directly apply it to our system. So once we have the predicted locations from the tracker ready, we only need to run the large detector model on selected regions, therefore greatly reduces the computation cost. But that comes with a problem. The problem is that if there are some new objects appearing mid of the stream, then our system is blind to it. So how are we gonna tackle this problem? Our solution is to add a small detector. And by small, it also means it's kind of inaccurate because accuracy always comes at the cost of computation. And the primary goal of that detector is to look for new objects. But when it is looking for new objects, it may also come up with some detected objects from previous tracker. And fortunately, our system is able to handle this situation because there is a step called non-maximum suppression in our big tracker, or big detector. And in this step, duplicated proposals will be filtered out. And we now put it together and name our system Cascaded Track Detector and give some new names to each component. The small detector is renamed as proposal network because it's a very small model running on the whole images. And all its detections is just proposals, which will be later calibrated by the refinement network. And the refinement network, although it shares the same parameters as the original large detector, it only runs on the part of the image and mainly does calibration. And the tracker predicts new locations from previous detections. And as you can see here, the proposal network and the tracker are both quite small compared with the original large detector, and they incur little overhead. And in this slide, we describe some details about the CaTDet system. So first, we will need to mention that the design principle of the system, which is modularity. And by modularity, we mean that CaTDet is designed in such a way that we can change a module without retraining the whole system. Notice that this is a little different from the popular end-to-end concept in deep learning community. By end-to-end, we mean that we can put some fancy components together and train them all together. But if you made some simple modification to any of them, then you will need to change the whole system again. And modularity is a desired property for a system because it will add great convenience for deployment and development. And it should also be able to support various detecting and tracking algorithms. So below, we show some default choice for our system, but it does not mean we are only limited to this choice. So for the tracker, we choose the sort algorithm, which is a very lightweight tracking algorithm because, as we have mentioned before, we only care about the rough location of previous objects. So we don't need it to be super accurate. And it is quite lightweight, so it can run 1,000 frames per second on a single CPU core. And for the proposal network, we choose faster RCN with a customized 10-layer ResNet, which is much smaller than a standard ResNet 50. And for refinement network, we use a standard ResNet 50, but it only selected executes on part of the image, and there's no region proposal networks because we already got proposals from the proposal network and the tracker. And it saves about 12 times number of operations on Kitty dataset. So here is an example from Kitty dataset to show how our system actually works. And so this is the last frame where we already got some detection results. And in the next frame, the tracker, by information of motion or other stuff, predicts some new locations. Notice that there are only 3 objects, and 1 object is predicted to leave the frame, so it's deleted and not shown on this image. And then the proposal network proposes some candidates as shown here in the red boxes. And it detected 2 cars and 1 cyclist, and notice that the larger car has overlap with tracker's output. But our system is able to handle it because in the final refinement step, the refinement network selected run on part of the image, which is marked in the dotted box. And then the duplicated detections and non-existent detections are deleted, and the remaining detections are calibrated. So here comes to the experiments part. So we selected 2 data sets with common urban street scenes that is ideal for autonomous driving. And the first is Kitty. Here is an example of Kitty data set. And the other is city persons. I give an example here. And both datasets are quite small compared with some popular datasets for training deep neural networks. For example, there are only 8,000 images on Kitty, compared with 1.2 million images in ImageNet. So we need to overcome the training problem. So we adopt a 3-stage training pipeline, which involves pre-training the model twice. First on the ImageNet classification task, and then on the CoCo detection task. And we have to say that the lack of complex and frame-by-frame annotated dataset is a general obstacle in this research field. And if anyone sitting here is willing to share like 1% of your private dataset, we will be quite grateful, yeah. And in the following slide, we will show 4 selected experiments. The first one is to show that actually our system works and temporal information is helping with detection. So here, the accuracy is measured in mean average precision, which is a common metric for object detection task. And here the Cascaded system is actually CaTDet without the tracker. So basically no temporal information. And what about CaTDet without the proposal network? We tried it and it's too bad, so we didn't even bother putting it here. So as you can see here, the Cascaded system achieves decent MAP on Kitty dataset with less than 1% accuracy loss. But if we switch to a more difficult dataset like city persons, then the accuracy loss is non-negligible, which is more than 6%. And for our CaTDet system, on both datasets, it achieves little or no accuracy loss, while reduces the number of operations by about 10 times. We show that temporal information is necessary to preserve the MAP. And on our last slide, we only show the theoretical speedup, which is measured in number of operations. And on this slide, we want to show some real speedup on GPU platform, like Maxwell Titan X. So notice that this script is implemented with PyTorch by some untrained PhD students. So we still believe there's large room for improvement. And here, as you can see, the overall time is measured frame by frame by CPU, and our CaTDet system is able to achieve 2 times speed up compared with the original faster RCN. And if you only measure it by GPU time, it's close to 4 times. And in this experiment, we are going to show another metric, which is delay, and show how it correlates with the number of operations and the MAP metric. So delay is defined as the average number of frames taken from an object appears to it being detected. And we adjusted the choice of proposal networks and rank it from the largest to the smallest and show how it correlates with MAP. So here is some better visualization of the previous table. So here, the green line is the MAP metric, which stays as a constant almost all the time. And the red line is the delay, which increases as the number of operations going down. So that indicates, like, for video object detectors, preserving MAP is easy, while preserving delay is more difficult. So we hope that could provide some insights for future video object detector design. And in our final experiments, we would like to show, actually we can replace some component of our CaTDet and it still works. So we replace the faster RCN in refinement network with RetinaNet. And RetinaNet is a popular single-stage detection algorithm, which has fewer operations than faster RCN, but also its accuracy is slightly worse. And as you can see here, with RetinaNet, the CaTDet system actually improves MAP and also reduces the number of operations. So it shows that our system is well decoupled, and it also works with other detection algorithms. So finally, we would like to show a tiny demo here. So here, the upper one is the original faster RCN model. And while in the bottom is our CaTDet system, and we marked the number of operations here. And as you can see, for most of the time, it produces almost the exact detections. And sometimes it's even more stable. OK. So in summary, CaTDet is an efficient video object detection system that can reduce the number of operations by about 10 times and preserve MAP well, but meanwhile sacrifice a little delay. And it can support various popular detection algorithms. And for more information, come to see our poster at the poster session. Thank you.
Paper is open for questions. Can you please state your name and affiliation before?
Yeah, Minsik Cho from IBM. So very nice work. I have one quick question here is that, so essentially you said that you use like a sort algorithm, right?
Which slide are you
For
referring?
tracker.
For tracker.
Yeah. Which is essentially like, as far as I understand, that's essentially Kalman filter-based numeric optimization. Here, right?
Yeah.
So that's essentially Kalman filter. And which has a problem when you have some kind of, let's say, the temporary obstacle in front of objects. So I'm curious why, so in computer vision community, there are other very inexpensive object trackers as well, based on some kind of very small neural network. So I'm curious why you use a Kalman filter instead of other, let's say, the DNN kind of approach, which can deliver better accuracy.
Oh, you mean why I chose Kalman filter for the tracker?
Yeah.
OK, so as I have mentioned, we are interested in the rough estimation. So we don't need it to be super accurate. So, and the problem of running a deep neural network is that it will consume extra number of operations. So right now, the tracker is almost negligible compared with other networks.
So here main reason is that for computational efficiency, you stick to Kalman filter instead of a DNN kind of approach.
Yeah.
OK, thank you.
And actually, we used even a simpler method than Kalman filter. And with experiments, it shows that even a simple linear decay model works for the tracker.
All right. Let's thank our speaker.
OK, thank you.